Hello, let's go over the limit rules. Okay, assume that f and g have a common domain, the same domain that mirrors the domain given in the definition. So it's a sensible, let's just assume that d is a sensible domain and that c is a sensible point in that domain. Let's just assume that the limit x goes to c of f of x equals L, which is a real number, and that the g limit equals m, which is another real number. We get, and these are important rules, the limit x goes to c of any fixed real number r is r itself. Because if y equals r, if f of x equals r, that's just the horizontal line y equals r. And as x is getting arbitrarily close to c, we're getting close to r because we're equal to r all the time. R doesn't really care what the limit is doing in a certain sense because we're just always at r. So the limit equals r for all real for any real number r. That's true. For any r that you'd plug into this limit. And here is another idea. The sum of the limits, as long as the original limits make sense. Now, this isn't, things get dangerous later if L and M are not infinity, or they don't stand for any kind of infinity, so there's no danger. The sum of the limit equals the limit of the sum, or the limit of the sums is the sum of the limits, which is L plus M. Now, in the case of continuity, L would equal f of c, and g would equal g of c, and we would have f of c plus g of c. The sum of continuous functions is continuous, but that's not promised. We're not necessarily promising continuity, only the existence of the limits. It could be that both are continuous, it could be that neither are continuous, it could be that one is continuous and the other is not, but we would have to have both of them to be continuous to have the sum and difference be continuous. Now, if both original limits are continuous, the sum and difference will be continuous. Now, if the originals aren't continuous, then you don't know what's going to happen. The sum and difference could behave in a lot of different ways, and we have no promises anymore. Okay, and likewise, the limit of the difference is the difference of the limits right here. Now, and this isn't surprising, the limit of a constant times f of x is r times the original limit. And again, we're assuming the original limit itself exists and doesn't go to infinity. And it's okay for r to be 0 here. We just get 0 itself as an answer, And then the limit of the product is the product of the limits. Again, we're making this almighty assumption here, so to speak, that the f limit is L and the g limit is M. Everything is hinging on these, okay? Now, be careful here. The limit of the quotient is the quotient of the limits as long as the bottom guy isn't tending toward 0. As long as my bottom limit, M, that I'm tending toward does not equal 0. If it does, I have to do usually some algebraic cleanup or maybe some trigonometric cleanup or both. But as long as my bottom isn't 0, I can do this. Now, I cannot do this if my M equals 0, because I'd get 0 over 0, and that doesn't make sense. That's undefined. Well, it's undefined. But anyway, otherwise we're good. It's okay for L to be 0, just not M to be 0. But anyway, still important. The limit of the absolute value is the absolute value of the limit. And, of course, L equals f of c if f is continuous at x equals c. And now if p is a positive number, the absolute value of L to the p is, of course that equals L is this limit, so that's just naturally equal to this limit to the p. But what we're going to say without proof, guys, is that we can take the limit out. The limit of the absolute value of this absolute value to a power is the limit of f of x, all raised to the power, is the limit, or the absolute value of the limit of f of x, all that raised to the power of p, the absolute value of the limit of f of x, all that raised to the power of p. We claim, and we're going to say it without proof, and it is true, that equals the limit x goes to c of the absolute value of f of x to the p power. So we can yank the limit out. And that's a nice thing to be able to do. Again, this is all assuming that this f limit up here exists in the first place, okay? We're still we're still under this umbrella up here. We always will be unless I say otherwise. okay, and tell you it's time to move on from the umbrella. If j is a positive integer, then L to the j is, well, of course it's equal, by definition, it's equal to this limit to the j, but, but here's where the boldness comes in. We claim we can, and it's true that we can indeed yank out this limit. The limit of f of x to the j, the limit of f of x quantity to the j power is just equal to the limit of the j power of f of x. Now, if j is a negative integer, and if L does not vanish to 0, then L to the j, then this is still true right here. Now, j would have to be a negative integer. It's a little dangerous for j to be a non-integer. We don't want to use complex numbers and all that. That's a long story we don't want to get into. So if it's a positive integer, even if L is 0, now if L is not 0, it still pushes through for the negative integers, because it doesn't make sense to raising 0 to a negative power is undefined, by the way. But anyway, if j is odd, then L to the 1 over j is naturally equal to this, and then you can just yank out the limit here. If j is even, and if L is positive, and I mean strictly positive, then L to the 1 over j is naturally equal to this, but the boldness is we can take out what we claim we can do, and I state without proving, is we can take out this limit. In analysis, you'll prove some of this. You'll prove this from here to here. Now, from here to here is just definition. There's nothing to prove. From here to here, there is something to prove, but this is an analysis, and I don't want to prove it now. So we can take out the limit. The above rules are, of course, good if at x equals c. If it just so happens that L equals f of c and m equals g of c, then we're continuous, and we can replace L with f of c and m with g of c. But now, in general, though, these rules are still good, even if that's not the case. Even if continuity does not hold at c, we're still okay. These rules are still good. Now, if I replace all those limits above with one-sided limits, either here or here, they still push through just like they would have. And if I replace them with limits as we go toward positive or negative infinity, they still push through just like before. I don't want to go relist them. You just go up here and you would just replace these little c's down here in the subscript with c minuses or c pluses or positive or negative infinity. Everything still pushes through, but I don't want to go through and retype all that. Just ditto for these, okay? I just want to save my sanity. Let me stop the video here, and in the next video I'll go into some examples, which it's about time. That's where we learn a lot anyway. Thank you. I'll see you on the next video.